Hey guys, this is video 9.8. We're going to talk about specific heat and what that means, kind of the notes that go with it, and then in video 9.9 we will do the calculations that are associated with it. So let's jump right in. We're going to be on page number 15 in your packet. Make sure you have your reference table out as well as we go through this video, and a calculator. You'll want that for the next one. There's one problem that we will do here in this, so make sure you have a calculator as well. So have those resources so that we can streamline this and kind of get to where we need to be. So, all right, specific heat. First things first, what is temperature? This should be an easy question that you should by now be able to answer. If you can't answer this, you need to go back and study and look over all the terminology and kind of the first half of this unit, or the first part of it where it's dealing with all the KMT and all those pieces. Okay, this is something that you will have to know, and it should be pretty easy. It's the average kinetic energy of the particles. Okay, so it's how much they're moving. That's really what temperature is. The faster something is, the higher the temperature is going to be. So there are 3 temperature scales. This should be pretty easy for you. You guys should be able to fill this out without me even helping you. But we've got Celsius. And the unit for that you should know is degrees C. We have Kelvin. These are the 2 that we use in this class. There is Fahrenheit. We're going to put it here just because, hey, we know it, but 98% of the world do not use Fahrenheit. We and only 2 other countries actually use, so do not use Fahrenheit. We will only be using these. And specifically, I want to kind of put a star there right now and kind of highlight it. This is the guy we're going to need for all of our energy calculations. Okay, so in the next video, when we're doing all of our conversions or our calculations and solving those problems, our temperatures have to be in Kelvin. Okay, and we'll talk about why that is as we go throughout. A calorimeter. This is something you guys are going to be using in lab if you haven't already used it by the time you're watching this video. This is just an apparatus that is used to measure the amount of heat involved in a chemical reaction or other processes. So I'm going to summarize that definition right here. So it's an apparatus. Oops, don't know why I spelled it like that. Used to measure the amount of heat involved in a chemical reaction or other process. Okay, we are going to use it talking about chemical reactions. So if you are watching this before the Cheeto lab, this is what we're going to build and we're going to use to figure out how many calories are in a Cheeto and kind of compare that and see if the nutrition facts actually are right. And it's used for other things as well, but we won't worry about it. We're going to use it for that energy transfer and how much energy is within it. So that kind of brings us to the next idea or question: what's heat or energy? So energy is a energy and heat is a form of it that is proportional to and associated with molecular motion. So energy, all right, is a / heat is proportional to and associated with molecular motion. Shouldn't be anything brand new to us, okay? The unit that we will use in science is a joule. You may know, you may have heard of like calories. Okay, and we'll talk about calories in a few minutes. We will be using joules in terms of our energy. We can convert between them, but joule is the standard SI unit. So there are temperature conversions. This is how we go between Fahrenheit, but we're not even going to worry about this. So you can cross that out, guys. We're not going to be ever dealing with Fahrenheit, so you don't need to worry about that. Kelvin, though, we have to be able to convert between Kelvin and degrees Celsius. Notice this is in your reference packet. If you look on table T at the very bottom, and I want you guys to flip to there now, it is the last conversion that's in there. So if you're trying to get to Kelvin, you take your Celsius and add 273. If you're trying to go from Celsius to Kelvin, you're going to subtract 273. So here's what our temperature scale is going to look like. kind of all of them split out. But again, remember, don't worry so much about Fahrenheit. We know that, or hopefully we know that. Maybe not the lowest temp, but if you take a look here with Kelvin, notice how 373 is the boiling point for water in Kelvin, and it's 100 degrees in Celsius. We know, or probably are familiar with degrees Celsius, and then the freezing point is 0. But notice how we changed 100 degrees here with Celsius. Notice how we changed 100 degrees with Kelvin as well. Sorry about that. So we can say that every degree, if we change 1 degree in Celsius, we're going to change 1 degree in Kelvin as well. They're on the same scale, but why are there two different scales? You're probably asking yourself. Well, notice how the lowest possible temperature for Kelvin is 0. This means that Kelvin values can never be negative. And this is very, very important, because as we're doing energy calculations or we're doing temperature change pieces, we can't ever have a negative value in terms of volume. So when we get into our next unit on gas laws and we're doing some calculations where we have volume and temperature in the same formula, we can never have a negative temperature, because that would give us a negative volume, and we can't have it. So more about that in the next unit, but right now, that's one big thing about Kelvin, is that it can never be negative, because absolute zero is when molecular motion stops. So we can also see that, hey, for every 1 degree Kelvin equals 1 degree Celsius. If I change my Celsius temperature by 1 degree, I'm also changing it by 1 degree Kelvin. Okay, so a couple big things to kind of keep in mind as we go throughout this unit as well as the next unit. All right, continuing on the next page. All right, heat and energy. Remember that heat is one form of energy, and the terms are often used interchangeably. So heat measured in Q, or capital Q, we'll see when we get into our formulas in the next video, is the energy that's transferred to a difference in temperature. Okay, joule or calorie. Joule is what we will be using most. If they ask you to figure out something in calories, they would give you this conversion factor right here. Okay, so 1 calorie equals 4.184 joules. Fun note of the day, kind of your fun fact of the day, is that food calories are actually kilocalories. That means 1 food calorie that you see actually equals 1,000 chemical calories. So when you eat something that says, oh, it's 150 calories, it's actually 150,000 calories. Now, I don't say that to kind of freak you guys out about how much you're eating and if you're counting calories or whatnot. All that is to kind of show you how much energy your body actually needs. So when they say something like 2,000 calories a day for your body, that's actually 2 million calories. That means that your body is consuming a lot of energy. Okay, so it takes a lot of energy. So let's do one quick example to kind of convert between the two, and then we'll kind of wrap this video up. So we've got 686,000 joules that are in a potato. We want to figure out how many calories there are. Simple conversion. Joules on the bottom, calories on the top. If I look up here, all right, we have 4.184 joules, 1 calorie. Joules cancel out. So all I'm going to do is divide by 4.184. I'm going to round this to correct sig figs, which would be 3. 164,000 calories in that potato. Now again, these are chemical calories, not food calories, which are kilocalories. So if we were to convert that to what we would think, oh, in a potato, there's about 164 kilocalories that are in it. Okay, so last thing to talk about is specific heat. Specific heat, guys, is just by definition, it's the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. Size of the degree divisions we just talked about are equal. So it's how much energy it takes to raise that substance, 1 gram of that substance by 1 degree Celsius. This is an important piece when we start doing those calculations that we're going to talk about in the next video. Notice that specific heat is constant for a substance. You guys are given on table B in your reference packet, you are given the specific heat for liquid water. Notice I say liquid water because ice, which is solid water, and gas or vapor water has a different specific heat, so phases do determine that, but we're only going to really be interested in water liquid form in this class. This is in table B, so again, make sure you look at table B and know where it's at. Okay, so that's kind of the basics behind heat and energy, guys, specific heat, and then we're going to apply that in terms of calculations in the next video.